Good afternoon. First, I would like to thank Barbara and Alexander for the invitation and for having me here and for the opportunity to show some of the work we have been doing to elucidate what will be the seismic signatures of volatiles in subduction zones. So basically, what are the features that characterize hydrous phases in the slab, if there are any, and that will help us to identify seismically the hydrated regions in subducting slabs. The whole idea is to try to put constraints on how much water you could subduct and how much water you could have in the mantle by comparing the physical properties of minerals with seismic observations that I will review. This is work I have been doing with a colleague, Sebastian Merkel, from the University of Lille, and a former graduate student, Angelica Rosa. So why we need to understand how much water is subducted and transported in subduction zones is because this is part of a much larger scale process that is the global deep water cycle that involves exchanges of hydrogen between different reservoirs like the oceans, atmosphere, and the mantle. And these exchanges of volatiles, mostly hydrogen, is critical for the evolution of the Earth interior because the reintroduction of water into the mantle, if happens, has important implications for the rheology of the mantle, thermal convection, and so on. So the idea is that a part of the water that might be subducted is not completely devolatilized in subduction zones, and we know that the balance between what is subducted potentially and what is recovered in volcanic arcs indicates that it might be like one-third of the water that might be still going deeper into the mantle and potentially stored in the region between 410 and 660 kilometers depth. That is what we call the transition zone, and which is a water storage site in the mantle. Whether we have deep water transport or not, we can discuss that, but there is some evidences for circulation of fluids at depth, which are much larger than the 200 kilometers we have been discussing these days. And these are evidences, for example, from seismic observations, and this includes, for example, the low velocity zones that are observed in the Pacific slab, above the Pacific slab that correspond here, that might be due to the infiltration of fluids and dehydration fluids at depth already on the transition zone. We have also evidences for dehydration melting at the top of the lower mantle. Here you see a cross-section across the US, and you see here clearly the 660 discontinuity, and here this patch shows anomalous velocities that might be related to dehydration melting because the ringudite will release the water that is not compatible with the perovskite that is in the shallow upper mantle, and lower mantle, sorry, and it will create a region where potentially melting is possible. There are other evidences for potential influx of fluids at depth, and this is the high attenuation region that is observed below China at the depth of the transition zone that might be related to the dehydration of a stagnating slab, which might influx fluids that they will be stored in the transition zone because the water, again, is much more compatible with transition zone minerals than lower mantle minerals. So now the question is, these are all remote observations for potential circulation of fluids, but the only direct evidence for water in the transition zone depths comes from this sample recovered in 2014. There is a diamond showing a very, very tiny inclusion, around 60 microns, that correspond to hydrous ringudite. So this is a phase that it has been assigned around 1.5 weight% of water, and this is included in a diamond, and this means that this diamond might have formed at least at 450 kilometers depth, and it's probably the first evidence that water might be, or that the transition zone might be hydrous, at least locally in regions close to subducting slabs. And it has been this year another discovery of another diamond showing inclusions of ice 7, so a high pressure phase of ice that could be also showing deep circulation of fluids. So we have potential clues for identifying hydration in transition zone, but there are still many open questions. And one of them is how water is transported in subduction zone. What will be the minerals carrying the water if the slab is hydrated? What is the degree of hydration of the slab? And how deep the water can be transported beyond the transition zone that we have evidence. And finally, what is the fate of water in subduction zone, how deep it can go? I will focus today mostly on these two questions, how hydros are slabs, potentially, and how deep the water could be transported. And I will try to answer that using mineral physics experiments. Briefly, I will introduce what are potentially the water carriers, but I think this is the topic of the next talk, so I will not go into many details. So just if you want to transport water quite deep into the transition zone, you might need to rely on the hydration of deep portions of the slab. So you still need to invoke deep hydration of the slab and the lithospheric mantle underneath the crust. And I bring again the picture that we have seen a couple of times already during the talk, during the workshop, from Manuele Faccenda, where he suggests that faulting in the subducting slab, when the slab is cold and old, it might allow for the infiltration of water, seawater, quite deep, including down to 30 kilometers depth. And along these faulting areas is places where the fluid will interact with the lithospheric mantle to produce hydrous phases. So the hydrous phases, if they are produced, they might be heterogeneously distributed along these faulting areas. And what are the minerals or the phases that you could grow in these environments under high pressure and high temperatures? These are minerals that have been discussed, or phases that have been discussed already this morning here, and these are the so-called dense hydrous magnesium silicates, and particularly the alphabet phases. And these are the phases that you identify in experimental studies, petrological studies, in the very simplified system, magnesium, silicon, including also some aluminum sometimes, water system, which is a very simplified view of the lithospheric mantle underneath the crust. So just focus on this blue area. This is the area where these hydrous phases that are formed in the lithospheric mantle might be stable. I think Professor Ohtani will discuss more in detail later. But these phases, they will be only stable along cold or very cold subduction geotherms. And they will form after the breakdown of antichorite in cold subductions, and you have a series of phases that will bring or allow for the transport of water quite deep into the lower mantle. These phases are only identified so far in experimental studies, but just show here what is the potential water storage of the different assemblies that you will subduct. You have here this 4-way % correspond to the water amount that an assembly produced by the decomposition of antichorite having phase A and orthoenstatite or enstatite will carry deeper into the mantle. And this is important because this is one of the constraints we will use later to estimate how hydrous can be the lithospheric mantle. So now, if we want to identify how hydrous slabs are, we rely on the interpretation of seismic observations, but for that we need, again, as I mentioned, the physical properties of these hydrous phases. And here I just summarize or identify the stability field of these hydrous phases and some of the seismic anomalies that have been identified around or within slabs. And these include low velocity zones and anisotropy, high anisotropy around the slab, on the back of the slab, and in some cases in fragments of detached slabs. And today, I would like to discuss mostly how we could identify or interpret these anomalies in terms of hydration in the shallow lower mantle or within the bottom of the transition zone and also at the shallow transition zone. To do that, we need information on the seismic velocities, compressional and shear waves, sometimes mostly shear waves because they are much more sensitive to hydration effects. We also need elastic moduli and how they vary with pressure and temperature conditions. And we also need information on the elastic anisotropy of these phases. On the other hand, we also need to know how are the textures developed by these phases to understand how they will create these seismic anomalies. And this data can be obtained in laboratory by combining different types of experiments, including Brilliant scattering spectroscopy or radial X-ray diffraction that I will introduce in a few minutes. So I will focus particularly on what happens on the bottom of the upper mantle and transition zone, shallow transition zone, and also what happens deeper below the transition zone. And for that, I will introduce briefly the experimental studies that we do first using Brilliant scattering spectroscopy to constrain the seismic velocities and anisotropy produced by hydrous phases at high pressures. So just briefly, this is the setup we are using to conduct Brilliant scattering experiments. I don't know if you're very familiar, but this is a technique that allows us to measure seismic wave propagation in materials. So it's like if we were doing indoor seismology. So we will use the inelastic scattering of lasers, light, optical photons, scattered by acoustic phonons or vibrations in the materials. And this will bring us the information on the propagation of waves, elastic waves in the material. So here you have a sample that is ready for the measurements, and this is the setting where we can change the orientation of the samples to constrain velocities along different crystallographic orientations to determine what is the anisotropy of the samples. So, of course, these experiments, we can do them at high pressure, combined with diamond anvil cells that you have here represented. Here is just illustrating how the laser goes into the sample that is contained in a metallic gasket, and then here is the scatter light that contains the information about the speed of seismic waves or elastic waves in the material. And what you have here is a sample in the diamond anvil cell, so you are looking at the sample by the top of the diamond. The samples are single crystals that are synthesized in multi-anvil apparatus, are prepared, and they have to have high quality to avoid cracks and so on that will produce misleading results. And it's embedded in a pressure transmitting media, and we have different rubies that are used as pressure markers during the experiments. So we can rotate the sample and probe different velocities along different crystallographic orientations, which means that we can obtain information on the anisotropy of the material. This is just an example of a typical Brilliant spectra that you will have, which is showing the elastic scattering that is scaled down. This is usually much, much higher in intensity. And then you have here the shear waves of our sample. This is a crystal of phase E, one of the hydrous phases that we might make in the slab. And what you have here is methanol, ethanol, water mixture that is used as pressure transmitting media. We have the compressional waves, which are faster than the shear waves. And also we have the contribution from the diamonds, because we will probe every material that we cross through with the laser. Just briefly, we measure the velocities along different crystallographic orientations, and this gives us an information of the anisotropy. And particularly these hydrous phases, they are layer structures, most of them, and therefore they are a potential source of anisotropy in subducting slabs. This is the structure of the phase E. We can use this data here to invert for the full elastic tensor and aggregate properties at high pressures and at high temperatures sometimes. And what you can also calculate, some of the symbols are looking funny, is the anisotropy that you have in the sample. Elastic anisotropy, in this case, this is the shear wave anisotropy or azimuth anisotropy, and you can see increasing pressure, the velocities increase, but the anisotropy is decreasing as we compress the material. And We have done that for several hydrous phases that are candidates for carrying water in the slab, and I have here a plot showing the shear wave velocities as a function of pressure. I think this is the picture Sergio was asking for this morning, where we see the effect of pressure on the anisotropy for, in blue, the hydrous phases in the slab compared to some of the major phases that you will make in a lithospheric mantle or of Habsburgitic or pyrolytic composition. The important thing is to note that hydrous phases, they have much higher elastic anisotropy than the dry samples in the slab. Particularly, I highlight here the regions above the transition zone that I will discuss in a few minutes, and also the bottom of the transition zone, where phase Z and phase D are stable hydrous phases, and you can see that their anisotropy is larger than that of, for example, hydrous Watzleite or even perovskite or ferropericlase at these conditions. So they will be much more anisotropic, and if there is anisotropy, they are much better candidates to explain the anisotropy than the dry phases will be. We can also constrain the shear wave splitting, or the degree of splitting in the sample, and it was mentioned already this morning that these phases behave a bit pseudo-hexagonal, and here you have phase E showing this behavior. Another information that we can obtain is how this shear wave and compressional wave of hydrous phases compare with the anhydrous components of the slab, because this will be the key to discriminate between hydrous and anhydrous region in subduction zones from seismic observations. And you have here the compressional wave, the shear wave, the pressure. This is delimiting the transition zone, upper mantle, transition zone, lower mantle. In blue are the hydrous phases, and if you notice, they are always seismically lower than the anhydrous, with the exception of ferropericlase in the lower mantle. So the hydrous phases, they will always display lower seismic velocity than the major anhydrous counterpart in the slab. However, if we want to identify hydrous regions in the slab, we need to see what is the effect of these hydrous phases in the global slab composition. And with this information, we can now model what are the densities, seismic velocity, and seismic velocities of subducted lithologies in between 180, 800 kilometers depth, which means 6 to 26 gigapascal, and we do that along cold slab geotherms. We will consider two types of lithologies that will be pyrolytic and Habsburgitic compositions with variable water contents. The water content, it will be vary between 0 and 4 weight percent, because, as I mentioned before, this will be the upper limit for the amount of water, which corresponds to the water carried by the result of the decomposition of anticorite in the slab. So the assembly of phase A plus enstatite carries 4 weight percent of water. So when you start subducting the slab, if it's hydrated because the water released by anticorite is caught by this assembly, you have upper water content of these in the slab. Now the question is how we distribute the water in between phases. So we need to make some assumptions. I calculate what will be the saturation water concentration or solubility of water in olivine at cold conditions. It's about 0.2 weight percent. This comes from the model of Bali et al. And now the problem is how to distribute across the transition zone the water. And there are values, a range of values for the partition coefficients of Watzleite and olivine that range from 2 to 6. So this means that depending on how much water you have at the beginning, you will, depending on the partition coefficient, you will put more water in Watzleite, and once you have water in Watzleite, you prevent probably the formation of other phases, because we don't know the partition coefficients. So we will assume that first, if we have water, we will saturate the anhydrous components, and the leftover water, it will be used to grow hydrous phases in the slab. So this means that if we have modal, I just illustrate what will be the modal proportions of Habsburgitic composition with 2% of water. We have in the upper mantle, we will make around 18 volume% of phase E. If we have this amount of water in olivine, where the other hydrous phase will be phase E. If we go into the transition zone and we assume a partition coefficient of 5, we will make around 13 volume% of phase E. And this means we have 1% of water in Watzleite, hydrous Watzleite. If we decrease the partition coefficient, all of these are range of values that are in the literature, so I might need to consider them. We will make a slightly larger amount of phase E because the water amount in hydrous Watzleite is going to be lower. So we can now compute what are the seismic velocities and the densities, and particularly, as I mentioned, I will focus on the region above the transition zone and right after the 410 discontinuity. And what you have here is the plot, the contours for the shear velocity contrast between a hydrous and anhydrous lithology. And you have here all the calculations I have done at 800 degrees, which correspond to a relatively cold slab geotherm. And what you have here is the hydration degree of the plate, or the lithospheric mantle, and here what you have is the velocity contrast. So if we have around 2% on the Habsburgitic composition, in the upper mantle, phase E will coexist with olivine, and you need around 2% of water to be detected seismically. The anomalies that you will produce are around 1.5%, what I think is already into the range of what seismically it can be resolved. In between. Shear velocities, yes. No problem. I put only the shear velocities. The contrast for the compressional is slightly lower because normally shear wave velocities are a bit more sensitive to hydration than compressional waves. So we will need to make detectable hydration. We will need to have around 2% of water in the plate. However, if we go into the transition zone, in black you have the results for the partition coefficient 5, so more water in hydrous Watzleite. I hope you can see in gray the partition coefficient 3. And what we need is, what we observe is that around 1.5%, you manage to make already anomalies of around 2% in velocities, which can be even much easier to detect. So hydrous phase E, it will be possible to detect seismically if it's present in the transition zone because it has a very distinct seismic signature compared to the anhydrous counterparts. And I also would like to remember or recall that it's also a potential source of anisotropy. This morning there was some discussion about anisotropy in the upper transition zone that could be also potentially related to this phase that is much more anisotropic than olivine, with which is coexistent, or even Watzleite in the transition zone. So water could be detected in the bottom of the upper mantle and also in the transition zone. But now I would like to go a bit deeper and try to see how deep the water could be transported and potentially whether we can interpret some seismic anomalies that are observed in regions like Tonga in terms of hydration degree, and in that case, how hydrous will be the slab. And just to recall, this picture that has been also shown a couple of times during the workshop, this is the configuration for the Tonga slab, where apparently there is a fraction of the slab that is detached from the main slab, and it's lying subhorizontally in the mantle. And this region is a big source of earthquakes. And also, we see that there is a 3% velocity anomaly compared to the surrounding mantle. And also, across this transition zone fragment, you will have an increase of the anisotropy, reaching values of around 1% at the bottom of the transition zone, with a particular polarization of the waves, where horizontally polarized waves arch faster than the vertically polarized. So the idea is that there might be a petrofluoric anomaly in the core of the detached fragment of the slab that is buoyantly staying in the mantle. And now the question is how we can produce such amount of anisotropy. Well, we need to see how hydrous phases, if they are the source of this, they will be deformed plastically. And for that, we do the other type of experiments where we combine X-ray radial diffraction at the synchrotron with diamond anvil cells to deform materials at high pressure and high temperature conditions. And this is schematically how it works. So we will put the samples, polycrystalline samples, and we will deform them uniaxially in the diamond anvil cell. And the problem is that we don't have any control on the axial deformation, as we could have in other type of setups, but we can deform at much higher pressures than it can be reached with other conventional methods. Then we will X-ray the samples, but not in a standard configuration, but through the gasket material, and then we will monitor how the Debye ring's intensities change with the azimuth angle. If we look at that through the axis of the diamond, which is the compression axis in this case, we can see the sample here, and then we have a piece of gold that we use as a pressure standard. So with these experiments, we can constrain the strength of the material and also the development of lattice preferred orientations, which will give us information of how texture is the material at the lower mantle. These are some of the results, and here you have the diffraction pattern at room pressure. You can see straight lines, almost uniform in intensities. However, when we go to higher pressures, what we see is that the fractions of the diffraction ring, they have developed modulations. And these modulations are indicated of lattice strain in the sample. And we also see changes on the intensity depending on the azimuth angle. What means is that the sample is textured. We can define we can treat these patterns. This is the refined patterns. We can obtain the strength and also the orientation distribution functions to model the textures later on. And I will show you here now what are some of the textures that we have found for this phase D, which is the stable phase in the lower mantle, the hydrous phase. And these are the experimental textures. We can see that the axis align that is aligning parallel to the compression axis is the 001 axis. And then we see that this stays until around 20 gigapascals, where we start seeing the development of a second maxima in the system. And we can interpret these textures first quite intuitively. The basal texture or the basal slip activation is related to the layer structure of the sample, but to identify what is the mechanism for the activation of these other textures, we need to model the deformation of the grains of phase D, and this we do that with the viscoplastic self-consistent modeling, and we can reproduce the experimental textures if we combine basal slip system with pyramidal slip system. And just to illustrate how it looks like, this is the crystal structure of phase D, another layer structure. We have basal slip, pyramidal slip. What means is that under pressure below the transition zone, phase D will have the basal, the grains with the orientation of the basal of C-axis parallel to the compression, or the 1,0 - 1 parallel. So we can use this information together with the strength, which shows us that phase D is the lowest strength phase in subducted lithospheric mantle compared to MgO, ferropericlase, or even calcium perovskite. So it will act as a strain localizing region if it's present in subducting slabs. So we can just go and model what happens in Tonga. And this is just a sketch showing the detached fragment with all the seismic anomalies that are observed and that we would like to interpret in terms of hydration. So we simulate what will be the anisotropy generated by a rock that contains phase D, as hydrous phase, the deep down compression regime of the slab. And this is what is the result. We have a sample, or assume a sample, that contains around 16 volume% of phase D, which means 1.2 weight% of water in the lithospheric mantle. And this is the water amount that you need to produce a velocity decrease of 3% that is observed in Tonga slab. With this composition, we can generate an isotropy that goes around 0.9%, which match pretty well with the anisotropy that is generated in subducting in the fragment of that is detached on the Tonga slab. So what I would like to say is this is just a configuration of the slab fragment. So if you have a wave probing the slab fragment like that, you will not see an anisotropy, but you will only see the anisotropy if you have a wave that is crossing this fragment in that direction. So what I mean is that you could explain all the seismic anomalies of the Tonga fragment if you have water in the slab and it's around 1 weight% of water. So I'm just going to conclude here, and you have here the summary of what are the best diagnostic features for identifying hydration in subducting slab by seismic methods. But my point that I would like to make now is that we have better and better mineral physics data about the properties of materials, but we also need more detailed structures of what happens in the slab. And I think the use of these guide waves that we have been discussing this morning, it could be a potential way of distinguishing between anisotropy coming from both sides of the slab or the mantle wedge from the anisotropy coming straight from the slab. That is what we need to test the mineral physics models in the slab. Thank you.